Welcome to the session. In today's session, we will learn certain basic terminologies of the control system, how a complicated system in nature or in our daily use can be represented in the simplest way using certain blocks, and the types of control systems. So today's layout is types of control systems. These are the two types: the open loop control system and the closed loop control system. Some most prominent terminologies used in the control system in practice throughout this course. Today we will define few of those, and we'll start with the block diagram representation when we are studying open loop control system. So friends, basically what is open loop control system? We can represent every machine or every process or plant or even a big factory in terms of a very simple time dependent function and a block. So here we have a block. So I can say that G is a function of T. This block will have certain inputs. Maybe you can say that U as a function of time is the input to this block, and output is Y as a function of time. Now this is the simplest example of a plant or a system which we use in our subject. So G is a function of time, and to run this machine or plant or function we need certain forcing functions, which is basically here we are defining as UT. This is the forcing function. Suppose you have a ceiling fan, you have to drive the ceiling fan, so you require certain inputs, forcing function of fuel. Here electricity is the fuel to drive the ceiling fan, so we apply certain voltage through a power system to the ceiling fan. So this voltage is basically your forcing function, that is UT. And when you are applying voltage to the ceiling fan, naturally you will get the rotation of the ceiling fan in RPM, that is defined as YT. But whenever we are speaking about the control term in control system, there is certain controlling phenomena. Suppose in the case of ceiling fan, you are switching on and off the ceiling fan, so that is how you are controlling the movement of the fan. Maybe some fan regulator you are using, which is a potentiometer, so it will change the application voltage and you can change the speed of the fan by setting the points of the potentiometer. In other cases, we need to use certain controllers or filters which will decide how exactly the forcing function should enter the process or the plant. Suppose I have to use a controller over here in the open loop system. So what I will do, I'm drawing the block again. This is the block, and you have the system as a time dependent function. But now the forcing function to the block will enter through another filter which is called the controller. This is again a function of time here, and here certain input will come. Now this input will be not the UT, but we say this is RT, because now we are defining it as the reference input. So here your controlling part goes, the control signal will enter the plant and you will get the output. This is the output of the plant. Now this is an example of open loop control system where certain input is given. you can see the difference between the nature of the inputs RT and UT. What is the difference? UT is the voltage applied to the ceiling fan, where ceiling fan is rotating, and you can record the rotation over here at the output. This reference input is basically an imitation of the output YT. We are imitating output YT and producing a similar kind of thing which is scaled, and this reference input will go through certain filter called the controller and generate the control signal. So here this is the reference input, this is the reference input, this is the control input, and this is basically the output. You have to see that in this situation the controller K is playing a definite role. It will produce a special kind of control signal UT based on the requirement of the design. Maybe we don't want certain kind of spikes in the input that should enter the plant GT. So we design a controller KT so that whenever you are giving a desired input, the controller KT is filtering the spikes and pushing in an input which is suitable to run our plant or our system. So this is an example of open loop control system. In open loop control system, if you see on the time scale, suppose I am defining the inputs and the response, that is the output on time scale. What happens? Suppose I am giving an input of this kind, right? So in the input, suppose there are some spikes like this. When the output is generated, so I desire the output should be following this line. Output should be following this line, but whenever the input is applied, the output is coming like this, and there are certain fluctuations. I don't want this fluctuation in the output, so I have to inhibit in the input this portion. Here for simplicity I am writing input, here is the output, and this spike or fluctuation is generating this portion, so I don't want this fluctuations in the output. So the filter, the controller K, will help me to remove this unwanted spike or ripple or fluctuation in the input. So that is the use of controller in open loop control system. Let us come to the case of closed loop control system, where the control system is not allowed to stay independent in case the output is produced and that output is not monitored directly. So here I am monitoring the output and manipulating in the system in such a way that the output is more or less closer to the desired input. How I can do it? I am redrawing it, the plant. So here I am putting a block. This is a block which is again GT, and this is the output YT. Then before GT I am placing the controller. You can see the controller in front of GT. Then this output here, it is measured, taken back and paired with the reference input in certain way. So the reference input RT is there, you have the RT, this is coming back. So as I am comparing, so this is plus, this is minus, so you have to subtract the measured output from the reference input. So when you are subtracting, naturally we are getting a difference. So this point we are defining as ET, the error signal. The output of the controller, as we studied earlier, this is UT. UT is also called the control signal, the output YT, the reference input RT. So whenever I am giving a reference input, some signal enters the controller, output is produced, then YT is measured. So YT is measured at this point and it is taken back through this path. So once YT is measured and it is compared at the input, so error signal is basically driving the controller. This is irrespective of the earlier case when the input signal was driving the controller and controller was driving the plant, but it was not monitored. The output was not monitored and compared. So here I am comparing the output with the input through this special mechanism. This is called negative feedback control system. We call it negative feedback control system. Here you will see that the reference input, the error signal and output vary in a specific way. Initially, when I am giving some input, this is the reference input, this is the error signal, and here you can see the output. So whenever you are giving the reference input, initially it is 0, so everywhere you will see 0. After some time, say at t equals to t1, input increases to certain value, but as the system is inertial, we will see that no output comes. But I can find here that error signal ET equals to RT minus YT. So error signal ET is developed at this point. Once the error signal is developed, it is following RT. Output gradually develops like this. And once it reaches a final value, the error signal will gradually reduce and become 0 in ideal case. So error signal is, at any point, error signal is the difference between the reference input, here you have the reference input, compared with the output. So you see the reference input is constant, but as the output builds from here to here, the error signal gradually reduces. So this is the beauty of the negative feedback control system. Whenever the output develops, the error signal reduces, but still there is a reference input. Now certain terminologies we will discuss. These terminologies are starting from system. We have already studied in the previous session that this is a series of interconnected tasks that work together to produce a result or certain outputs. Whenever we want to produce an output which is the desired output of our choice, then we use a controller, and the controller, when looped in the system, will produce a desired output. So all the inputs and outputs of a control system are defined as variable. So a system, basically I am asking that this is the bunch of tasks or processes or sub-processes which together produce a result which is of our requirement. So this bunch of tasks together, when it is producing a meaningful result, this is called a process, or this can be called a plant. So as we discussed earlier, whichever is the desired output you want to produce, you have to imitate the output and give a scaled input, which is called the reference input, or in different situation we call set point or command input. The process variable. So this is the output of the system. Because the system is called process, the output of the system is called the process variable. Some other names are also there. There is a control variable. The output of the system which has to be controlled is called the control variable. So this is called controlled variable as well. Another name is the manipulated variable. Now every system is designed initially to work in a nominal environment where there is no disturbance or where is no unwanted input to the system. This is when the system is being designed in the laboratory. Initial design is the nominal model of the system or nominal system when there is no disturbance. But as soon as you go to the field, you will see that there are disturbance to the system. Like if you are running a fan and I am saying that I want to reduce the speed at a given supply voltage, say 200 volt, its nominal speed is 300 rpm. I want to reduce it to 250 rpm. Maybe manually I am holding the rotor and trying to reduce the speed. So that is the situation of disturbance at the output. So these disturbances can be minimized if a controller is well designed for the system. And disturbance is always a low frequency phenomena. Noise is another kind of input to the system. Mostly it enters the system whenever we are trying to measure certain variable of the system. So it is a high frequency phenomena. The servo mechanism is basically, this is a kind of control system where the control variable is either displacement or time derivative of displacement or double derivative of displacement. So this is the displacement, velocity and the acceleration. And the last topic of today's discussion is the linear time invariant system. So linear time invariant, basically it is extracted from the actual system which varies with time and in which the parameters are changing, and system is as well as the non-linear system. So if we extract a model of a system where the parameters are not changing, that is the behavior of the system is not changing with time, that is the invariant system, and we are using the system for certain frequency range where the system is behaving linearly. So such kind of modeling will produce a linear time invariant system. So further studies will be made in detail in all these terminologies which we studied today. Thank you for listening.